week 4, problem 2. This problem asks you to address the same diagram as was done in problem 1 and use an alternative approach to prove that you get the same result. So in the upper left-hand corner, I've written the result from problem 1, which was that the sum of all moments was equal to negative 49 pound-feet. Now, the approach that they're asking you to take here is to resolve each of these vectors into their components, add all of the components so that you get one resultant vector, and then apply that vector to the moment arm and see if you get the same results. Let's consider that for a moment. So the first thing we'll need to do is vectors 3 and 4 are already in a good position in terms of they're purely vertical and purely horizontal, but we'll need to break vectors 1 and 2 into horizontal and vertical components. And so I will call this x1, I will call this y1, and what do we know? Well, let's see. We can relate, we know the length of the hypotenuse is 30, so ka toa. What function relates the side opposite in the hypotenuse? The sine function does. So sine of 60 equals y1 over 30. To get y1 by itself, multiply both sides by 30. So y1 equals 30 times sine of 60 degrees. And if we multiply that out, 60 degrees, we're in the sine mode, or we're in the degree mode, sine of it times 30. This vertical component is very close to 26. So y1 is equal to 26. The horizontal component, so now we want to relate adjacent and hypotenuse, so we're going to use the cosine function. Cosine of 60 is x1 over 30. Again, to get x1 by itself, we multiply both sides by 30. 30 times cosine of 60 degrees equals x1. So we'll clear out of this. 60 cosine times 30 is 15 pounds. So x1 equals 15 pounds. And as we look at the length of those vectors, these appear to be reasonable numbers, 15 pounds. Now, for vector 2, I'm going to define x2 and y2. And again, we know the length of this hypotenuse is 40. And so we can say the sine relates the side opposite. Sine of, and in this case it's negative 45 degrees. Now it doesn't really matter. We can treat everything as though it's in the first quadrant as long as we keep track of sines by looking at the drawing afterwards. So rather than take the sine of negative 45, I'm just simply going to take the sine of 45 equals what? It equals the opposite, which is y2, over the hypotenuse, which is 40. So 40 times the sine of 45. So we'll clear out of this. 45, we're in degrees mode. Take the sine function, multiply it by 40. Is about 28.3. Now, as we talked about in the last problem, this vector is a special case because x2 and y2 are equal because it's a 45, 45, 90 triangle. So I can consider y2 to be 28.3 and the same thing for x2. So let's develop a free body diagram now that adds all of these components. So we have to the left this force of 50 pounds, and to the right x1 is 15, and x2 is 28.3. And the vertical components, well, we've got F3, which is 10 pounds.
Yeah, I know I do.
And we have the vertical components of Y1 and Y2, which are 26 pounds. So the vertical component of Y1 is 26 pounds. And the vertical component of Y2 is 28.3. Now recall, it's just simply a matter of kind of adding up all of the pieces. So if we think about what we'll get is we'll start a new diagram over here, and we're going to get one vertical vector and one horizontal vector. So if I think about the vertical components, it's positive 26 in the up direction, minus 10, minus 28.3, which gives me 12.3 pounds downward. And same process for the horizontal vectors. And again, to the right are positive numbers. So 28.3 plus 15 minus 50. So we end up with a leftward push of negative 6.7. So the first part of the question talks about computing the moment. Well, if you think about these two vectors, the vector that's acting straight left is axial to the pivot point. That is to say, it's directly aligned with the pivot point. So it doesn't contribute to the moment at all. So it's irrelevant. We need not consider it. Which means that all we need to consider are the vertical components. So the sum of the moments equal, and remember this is a negative number because it's in the downward direction, negative 12.3 times 4, which equals 48 plus 1.2, 49.2, and it's a negative number. So you can see that there's a slight rounding difference, but we arrive at the same vector. Two different approaches to solving the same problem. That's what they're really trying to get across here. The other part is, let's now resolve this into a single vector. So remember, to resolve multiple vectors into a single vector, we simply slide them head to tail. 6.7, 12.3, and we will calculate the length, and then we will calculate this included angle, and from this included angle we'll be able to get the actual heading of the vector. So the length is, I'll just put it as L, is 6.7 squared plus 12.3 squared by Pythagorean theorem. So, and actually I can just square this negative 6.7 because it'll become positive during the squaring process, plus 12.3 squared. Okay, so that is equal to the square of L. So now if we take the square root of that, that'll give us the force L, which is very, very close to 14 pounds.
I'll look at the essays. She's the one that looks at all the packets to make sure that they're right. So.
Now the direction, we have to use a trig function to get. And if you think about what we know the adjacent and the opposite. So we need a function that relates opposite and adjacent. So we know the tangent of theta equals the opposite, which is negative 12.3, again because it's in the downward direction, and 6.7 is negative as well because it's in the leftward direction. Well, remember we have to undo the tangent function to get this, so we're going to use the arctangent function, so tan to the negative 1 of this ratio. And we could drop the minus signs because they're both negative. So a negative divided by a negative is a positive. I'll leave them in there just to be clear, but you would not need to leave those in. So let's find that number. So 12.3 divided by 6.7, and then we're going to take the inverse tangent function of that. And what we find is this included angle here is about 61.4 degrees. Now, what you have to remember is that in the Cartesian plane, 0 degrees is straight to the right. So if we come up here and we draw the Cartesian plane, here's 0 degrees. We're at an angle basically 61 degrees past the x-axis. So this would be 180 right here. So the actual heading, as we're going to describe it, is going to be 61 plus 180. Again, because of rounding, the answer they get is 240. So basically the final vector, as we calculated it, 14 pounds at 241 degrees. Again, very close. This is just simply due to not carrying all of the digits to simplify the calculation in the explanation. So again, what you're to take from this is that there are multiple ways to solve this problem. You could resolve all the vectors and calculate a moment, or you could basically calculate the moment and then sum all the moments. Either way is a fine way, and you'll find for different problems, different approaches work better.